Nowadays, we collect more and more data in the steel plants. Thousands of parameters are tracked by sensors about production control, quality control, material logs, process logs, equipment wear, maintenance data, and so on. But how can we capture value out of this bunch of unrelated data? The difficulty is that some of the collected parameters are linked to a given timestamp. Some are linked to a material, which could have been cut or welded since that moment, and some parameters are linked to a part of the material even. Again, here it could be that the material has been cut or welded afterwards, and therefore the coordinates are not valid on the final material anymore. So the first step in order to use this data is to first link those data points together in a consolidated data model. Hello everyone, my name is Jeremy Kopp. I am responsible for the Planning Competence Center at PSI Metals. Today I will explain you how PSI Metals software can predict quality issues on your materials by using machine learning models. The PSI Metals software knows the full material genealogy and can therefore match the data to the right materials and even to the right zones of materials by doing the link between parents and child materials in the production route. And the PSI Metals production tracking knows what material was processed at a given machine at a given time. So PSI Metals software can help you to join all your data in a consolidated data model, which is then ready to be used by a machine learning model. When our data model is well consolidated, then we can look at the machine learning pipeline. Here you can see the defined pipeline. We first get the data. All data should be available at the prediction time, of course. If not, it's not useful to use this information in the training model, as anyway it will not be available for the online model. Then as a second step, the data preparation. So for example, if some data are missing for some sensors or some objects, we need to care for that and align all the data. As a third step, we train the predictive model. So by using a data set of training, we train the model. As a second step, we test the model and evaluate the quality. We choose also potentially the best model among the compared models. Later, we can use this selected model as an online predictive model. So it means that we get the real-time data from the production, and based on this real-time data, we can predict if this material will have a defect or not. And then, of course, we need to monitor the quality of the model in order to retrain it when needed. Here, what's very important is that we have a clear separation between the blocks. This enables us to have a higher flexibility, as we can easily replace a model by another one without affecting the complete loop of blocks in the pipeline. Also, it gives us the opportunity to extend easily the needs of the model or the needs of the business requirements without modifying every block of the loop. The problematic about defects is that they are mostly not visible directly after they have been created. In the shown application, we predict defects which originated at the hot strip mill, but which are not visible until the finishing lines. By knowing this defect earlier, we can save value and have a chance to act on it directly. For example, we can reassign the material to a less demanding order, or we can add a rework step to correct the defect. Anyway, saving time to know that there could be a defect on this material will also save value and give you chances to act on it. So what is the workflow? At first, we receive historical data. As previously mentioned, of course, we need to have consolidated data. And for that, we can use the genealogy model and the tracking so that all information is linked together. We have one consolidated data model for materials. We use this data set for training a machine learning model. Then this trained machine learning model can be used in the online environment in production. And when the data is sent in real time from the production, the online predictive model will be able to return a quality prediction. So that's the complete loop for the models to be used. So what is the data which is required for training this predictive quality model? Some data about the materials are needed, of course, like the chemistry, the dimensions, also some data about equipments or their maintenances, also about production logs, like for example, the roll pressure or the machine temperatures. These, by the way, are some time series. I will come back to that special case of data in the rest of my presentation. Also, some additional data is required from the production schedule, for example, to know how the different materials passed on the line, on the machines. Also, the ambient conditions could be relevant, depending, for example, if there are high temperature change between summer and winter or between the night and the day. But also some shift information could be valuable in the model. Of course, for training the model, we also need information about the actual defects of those materials. Even if they are not yet known at the outstrip mill, still we need to know what were the detected defects downstream for those materials. Of course, this is only used for training the model and not for the online model. The goal of the online model will be to predict this information. The extraction of data from time series is key to not lose information out of the data. In our first customer project, the customer initially provided sampled data, which means that they sent us the values of those signals taken every 5 seconds. So you can see here on the graph that the blue dots, which are just sampled data every 5 seconds, do not bring much information compared to the complete orange signal on the graph. Now we receive the complete time series and we extract from this time series some statistical features for each material. And what we can see is that previously with the sampled data, it had no influence on the prediction of the defects. And now, since we are using some statistical features extracted at the material level, and then these features have a contribution to improve the quality of the prediction. So it's very important the way you handle the time series data for your model. About the data sets, so of course the available historical data for the training needs to be split in two parts. First we have the training data set and then we have the test data set. This will ensure that the model can be tested on a data set which is independent from the training data set in order to approve the quality of the trained model. For the predictive quality model, we recommend to use a training data set of about 1 year. This is long enough to reflect the potential seasonal patterns, and also it's not too long to avoid using outdated circumstances. Indeed, the machines and the equipment could have evolved since 3 years ago. In this case, the historical data would bring wrong information. Indeed, the circumstances during the training must reflect the same circumstances during the online usage of the model. During our projects, we compared several machine learning models, and we found out that we don't have enough defect occurrences in order to use neural network with a high quality for the prediction. Here, in this case, we have only thousands of defects, but we would need actually millions of defects for training such a neural network. Also, another reason is that static features have a high importance in the prediction, and therefore the gradient boosting is a better model for this precise predictive case. Sorry. You can see on the graph on the right side that the calculated probabilities of a defect for each material. Of course, those probabilities remain globally very low, as the percentage of defects in production is only about a few %. And in order to use those calculated probabilities as binary predictions, we need to define a threshold. For example, if the probability of having a defect is higher than 50%, I predict that this material has a defect. So now, how can we define this threshold in a clever way? Based on the real cost of the actions to fix the defects and the real cost of keeping a defect, we can calculate the threshold value which is optimal to reduce the overall costs. It means that if the cost of action is low compared to the cost of defects, we want to act on more materials in order to reduce the number of defects. Of course, we also need to take into account the business or technical limitations for the related actions. For example, adding a rework step can fix a defect and has a low cost, but you cannot add this rework to all materials, as your machine has a given capacity. The gradient boosting model can also provide a feature importance for each feature of the dataset. This can bring high value to understand the causes of the defects and act on the engineering process in order to reduce the number of defects, independently from the online predictive model. The choice of the model is very important, as some models would be biased or would not be able to predict accurately an event. Here I would like to raise a warning that machine learning models cannot provide information where there is no information. For example, if you try to predict the quality of your materials for a given route, this can be biased. Indeed, the same materials or the same types of materials are using the same route. So you are using biased information, and therefore your prediction will be biased as well. Another example is if you want to predict something that happens very seldomly or almost never, machine learning will not be able to predict that. Indeed, machine learning is simply using all the information of your historical data in order to predict the future prediction. In case a defect never happened or very seldomly happened, we don't have enough information to really learn from this fact, and therefore the machine learning model will not be able to provide a good quality for the prediction. Of course, for some of those cases, there are some potential improvements where we can group similar materials or similar operations together to achieve route variation. At the end, what you need to keep in mind is that you need to carefully think about your predictive model and make sure that this model is not biased and that you have enough data and enough information to be able to predict this model. Another use of the feature contribution that I mentioned before is to monitor the model quality. Indeed, the model quality can reduce in time, and therefore it's important to monitor the quality in order to trigger a new training of the model if the conditions have changed. This will enable to increase the quality of the predictions again. In practice, we store the principal component analysis transformation of the training data, and we continuously calculate the distance with the principal component analysis transformation of the data for each prediction request. In this way, we can measure how far this dataset is from our training dataset. If this distance is above a threshold for many materials, then it means that we need to retrain the model. Thanks to PSI methods' predictive quality, you can take advantage of all the collected data, and you can act on the defects before they can be observed, and therefore save time and money.